Hello and thanks for using TickBoom. In this video I'm tackling part 3 of this 4-part question, which represents the final question on the 2020 Extension 2 exam for the New South Wales HSC. So if you haven't already watched my 2 videos on part 1 and part 2, I recommend that you do, because the nature of this question is that each part builds upon those that came before it. So it would probably be a bit hard to follow along if you haven't already got your head around the first 2 parts. For this part 3, we're told to let Jn equal the integral from 0 to 1 of x to the power of n 1 minus x to the power of n dx. And then we're told expressly, using the result of part 2 or otherwise, show that Jn equals n factorial squared on 2n plus 1 factorial. And you can kind of right away see that what we're trying to show here is very similar to what we worked out in part 2. The only difference is that in the numerator there's a 2 to the power of 2n in part 2, whereas that's disappeared here. So definitely working from part 2 is going to help us. The only question is, how do we do it? And I think this question is the first part where the real challenge of this final question shows itself. I think you really do need a bit of creativity here. So if I just write out what we're told that Jn is equal to the integral from 0 to 1 of x to the n 1 minus x to the n dx for n equals 0, 1, 2, and so on. And what we're trying to show is that j to the Jn is equal to n factorial squared on 2n plus 1 factorial. And I guess what we can make use of is that from part 2, we know that In is equal to 2 to the power of 2n times n factorial squared on 2n plus 1 factorial. So it's this 2 to the 2n that is the difference between the two. Now, where to go from here, actually, it doesn't naturally jump out at you. I think this really is where I would anticipate a lot of students might get stuck. But the key here is to try and convert the integral that we're given into something that looks like the integral that we worked from to get to this result in part 2. So just to remind us, that integral was, we were told that In is equal to the integral from 0 to pi on 2 of sine to the 2n plus 1 2 theta d theta for n is equal to 0, 1, and so on. So if we can get this integral into the format of this integral, then hopefully it wouldn't be a huge logical leap to get from the result in part 2 to the result in part 3 here. And we see that the integral for In has signs in it, whereas it doesn't for Jn. And so I think this is what kind of leads you to the idea that perhaps substitution could be a technique that could get us somewhere here. And so the question then becomes, well, what should you substitute? And realistically, in an exam, you'd probably have a bit of trial and error. But ultimately, if we let x equal sine squared theta, I think this is going to lead us to where we need to get to. So from there, we can know that dx d theta would equal 2 sine theta times cos theta, and that's just using the chain rule to get to that. So therefore, the dx would be equal to 2 sine theta cos theta d theta. So we know what we can substitute in here for dx. We know what we're going to substitute in for x. And so now we just need to convert these bounds of the integral. So when x is equal to 0, we'd get sine squared theta equal to 0, which would give us a theta of 0. When x is equal to 1, we'd get sine squared theta equals 1. And that really is sine squared theta minus 1 equals 0. So you get the difference of two squares. So you get sine theta minus 1, sine theta plus 1 equal to 0. And you get two solutions here. You get sine theta equals 1 and sine theta equals negative 1. So you get theta equals pi on 2 and theta equals negative pi on 2. But we'll just take the pi on 2 here. And the reason I kind of know that's the one I want to take is because I want an integral with pi on 2 at the top. So that's the logic there in taking that solution. So now what we want to do is just take our Jn integral and substitute in all these ingredients. So we'll get an integral from still 0 to pi on 2 of, we're going to insert sine squared theta for the x, so that will become sine 2n theta times 1 minus sine squared theta to the n, and instead of dx we'll have times 2 sine theta cos theta d theta. So now we need to try and get this into a format that can ultimately allow us to simplify this integral up into this format here. So the first thing I think we can do, this 1 minus sine squared theta, we can replace that with cos squared theta. So we'll get the integral from 0 to pi on 2 of sine 2n theta of, this will be cos squared theta to the power of n, so we'll get cos 2n theta times 2 sine theta cos theta d theta. And again, that's just using sine squared x plus cos squared x is equal to 1, using that result. I might have to turn over the page, but continuing this on, we'll get Jn is equal to, and I think we can, we'll bring out the 2 and we'll bring in the sine theta and cos theta, we'll bring it all together. So we'll get 2 times the integral from 0 to pi on 2. We'll first get sine 2n plus 1 theta. And then we'll get, and similarly we'll get cos 2n plus 1 theta d theta. Alright, so now I think this is where we get that moment of creativity required, because we want, in the end, we're getting close, but instead of a theta in here, we need it to be 2 theta. And I know there is a result. There is a result that I can rely on, such that I have sine 2x is equal to 2 sine x cos x. So if I can get this into that format, then I'll be able to say sine 2n plus 1 2 theta. So really where we've got x here, we're thinking if we can get that, we've got the thetas already, we want to get it to a 2 theta, so we need a 2 out here that's to the same power of what our sine is to. So let's just do it. Let's just get a 2 to that power. So if I go, I want it to be 2 to the power of, well, I've already got a 2 out here, so I can say 2 to the power of 2n, but if I want to multiply by that, I have to divide by that as well, times 2. times the integral from 0 to pi on 2 of sine 2n plus 1 theta times cos 2n plus 1 theta d theta. Now this 2 to the 2n times 2 will become 2n plus 1, and I'll bring that into the integral to make it really clear. So outside we'll have 2 to the power of 2 to the 2n times the integral of 0 to pi on 2 of 2 to the 2n plus 1 times sine 2n plus 1 theta times cos 2n plus 1 theta d theta. And that's now in this format. So I can use this result, 1 on 2 to the power of 2n times the integral of 0 to pi on 2 of sine 2n plus 1 2 theta d theta. So I've used this result up here, 2 sine cos, 2 sine cos, but everything to the power of 2n plus 1. So that then is our in integral. So now I can just put in in there, equals 1 on 2 to the power of 2n times in, which we know from part 2 is 2 to the power of 2n n factorial squared, 2 to the power of 2n n factorial squared on 2n plus 1 factorial. These will cancel and we'll get n factorial squared on 2n plus 1 factorial, which is exactly what we were being asked to prove. So really this moment here is, I think, the moment of creativity required to get this result. And I think it wouldn't be surprising that a lot of students might get caught up here, because first of all you need to think to use substitution, and there really isn't a clear reason or why you'd necessarily pick sine squared theta. You'd probably find yourself doing a bit of trial and error before you landed on this, but ultimately once you get there you are able to kind of just work through the mechanics. But even doing that, to kind of think, let's multiply top and bottom by 2 to the 2n to then be able to eventually cancel out, I think that's the out-of-the-box thinking that this question demands. So I was kind of waiting for it. I kind of almost expected it had to be somewhere in this question for it to be a final question of the 4-unit paper. And so here it is. So yeah, well that's really it for this question. Hopefully all of that you could follow along with. I mean, in the exam environment, whether I'd be able to think of that, I mean, I'm not sure. Again, having the luxury of time and just working through this kind of at my own pace, you can eventually get there. But I can see how this would be very difficult in an exam, and why many students might not eventually get it in the time that they're given. But that's it for that part. So now there's just one more part to go, which I'll cover in the next video. Tick boom.